Hi there, welcome to part 7 of Sound Basics. We're playing a little bit of YouTube Inception in this video because I have videos within videos within videos. A little while ago I made a video attempting to explain in a layman's way the Fourier Transform to those who don't have, like me, don't have a very strong math background. And the Fourier Transform is a sort of foundational concept in sound, in particular in electronic music or digital audio. So try to get through it and see if it's helpful to understand this foundational concept. Hi, welcome to this tutorial. We're going to try to give a layman's explanation to the Fourier Transform, the Fourier series, fast Fourier Transform, inverse Fourier Transform, and the many guises it takes, because we're going to start looking at some spectral effects. And even though, just for a practical implementation, if you can just follow step 1, step 2, step 3, you can make the sounds happen and you're happy enough and you can figure out how to modify them to your liking. It's sometimes good to understand a little bit of the theory behind it, just so we understand why certain processes need to take place and what exactly you're doing in transforming the music, say in Maxwell Supercollider or whatever you're doing, using these different objects, FFT object, IFFT objects, and such. All right, so I'm going to take sort of a very layman's approach. I'm not great at math myself, and a lot of this stuff might even be beyond me. So if I'm trying to explain it to myself, hopefully it will help other people without a strong math background understand what's going on. So this is gonna be kind of a meta tutorial. I'm gonna take a number of different videos, play some of them kind of in the entirety, and do maybe like a Mystery Science Theater kind of thing where I stop and interrupt or make comments along the way. Okay, so let's start with this introduction to the Fourier Transform, and I'll start playing it from this point, and then at a certain point I'll stop it and maybe try to clarify certain aspects of the video.
This first equation is called the Fourier Transform, or the forward Fourier Transform. This second equation is called the inverse Fourier Transform. And as you can see, the first equation turns a function of time into a function of frequency. And the second equation does the reverse. It turns a function of frequency into a function of time. And this process of turning one into another is called transformation, and so these equations are transforms. So what exactly is a transform?
So I'll stop it there and just simply underline this idea. We often talk in terms of FFT, Fourier Transform, or Fourier analysis. We talk about the time domain and the frequency domain. Okay, and as our host will go on to explain, they are really the same thing. They're just two ways of looking at the same thing. But just to underline the fact that we talk about time domain and frequency domain, and we'll get into the details of that with a couple other different kind of videos.
A transform is a mapping between two different sets of data, or domains. In this case, it changes information in the time domain into information in the frequency domain. Here I'm using the variable nu to represent frequency in units of hertz, or cycles per second. The data in these two domains look different and can even vary in length of the data, but it still represents the exact same information. For example, if I asked you to find me at the White House, assuming you knew where that was, that title would be all you would need to know to find my location. However, I could have also said find me at 1600 Pennsylvania Avenue, Washington, D.C., or find me at these specific GPS locations. Each of these descriptions represent the exact same location. They're just stated a little bit differently. And depending on your situation, one way of presenting the information might be better than another. And a transform would get you from one representation to another. And this is exactly what the Fourier transform does. It jumps between two sets of information. But instead of converting between two addresses, it converts between the time domain, f of t, and the frequency domain, f of nu. Now, Jean Fourier and others figured out in the early 18th century that any continuous signal in the time domain could be represented by a sum of carefully chosen sinusoids. And since sinusoids can in turn be completely described by their amplitude, their frequency, and their phase, those three parameters are all the information we need to know to describe the signal. At that point, we can plot the amplitude and phase at every frequency, or across the entire spectrum, and call it the frequency domain representation of the signal. And this information is exceedingly useful in control systems and digital signal processing. Of course, most signals aren't just comprised of a single sinusoid, but multiple ones at different amplitudes and phases across the entire spectrum. But why decompose a signal into sinusoids? Why not some other repeating signal like a square wave or sawtooth, or why not into different aperiodic signals altogether? Well, what we're trying to do is transform the signal into something that's easier to work with, at least for our particular purpose. And sinusoids are great because they're the only waveform that doesn't change shape when subjected to a linear time invariant system, or LTI system. There's a link at the bottom of the screen to a video that describes why this is true. Alright, so the benefit of having an input waveform that doesn't change shape is that it allows us to think in terms of change in amplitude, or gain, and change in phase through a system at any given frequency. And that lets us make use of a whole arsenal of tools for designing and analyzing control systems.
All right, so let's stop that there. And let's unpack this a little bit. This idea of simply, I'm trying to scroll up, of course, but I can't. This idea simply complex signal being a collection of sinusoids. So I have a couple animations that I want to get into here. Let's see. Let's start with right. Yeah, let's start with this animation right here. So actually I have a better copy of it here. So we'll look at this animated GIF and we'll see that we can take any basic signal and break it down to constituent sinusoids. Okay, so you take this kind of square wave, which is composed of adding signs, and you can break it out into its component parts. And you have their frequency, you can see by their speed here, and then their relative amplitudes to each other. So that's frequencies and amplitudes. Okay, and this is a basic idea of constructive and destructive interference. Sinusoids are nice linear systems. They add and subtract from each other in a linear fashion. Okay, so this is a nice little applet that might help us to understand this a little slightly better as well. So if I add certain sinusoids, so if I have if I change the amplitudes of these sinusoids, you can see the individual components, and then you see they sum into a continuous waveform. Okay, so when we're talking about the time domain, we're talking about really what's down here. We have the sort of complex or summed waveform that is represented by these individual components, and that's what Fourier and others postulated, that you can break down a complex waveform into a sum of its sinusoidal counterparts. So if I went ahead and started adding the sine waves or adding some amplitude, so here's another one at a different frequency with a different amplitude, you get this summed wave. If I add, just sort of kind of randomly did that, you get a summed wave that looks like this. Let's see if I can, get it all in there. If I add a fourth sinusoid there, you get this complex wave. It sums. If I add a fifth, you get that. About a sixth here, etc., etc. And so you see these component parts start adding up. And the individual component parts, so if I just say, let me just go back here. Sorry. Okay, let me just go back and see if we can see at least just do one add and subtract here. So here, this is negative and this is positive. So so these 2 points kind of cancel each other out, and the summed wave is kind of flat. And then here, they reinforce each other. These are two positives. They add together and it adds up here. So we can kind of do that. And here, again, they subtract, so you get this sort of waveform here. So it's a linear system. They add together and they subtract together in a linear fashion, right? So if we go ahead and add back up all our other constituent parts, they add and sum and subtract to create this complex, single complex waveform. But really, it can be represented by these component sinusoidal parts. So going back again to this animation, we can see that you have this complex square wave, okay? And it can be broken down into individual sinusoidal parts. These are the individual sinusoids. All right. The formula, according to that formula. And then broken out into its constituent parts. Each of these, eventually we'll learn, are described by their amplitude, their frequency, and their phase. Okay? And let me just, not to beat a dead horse or drive this point home too much, but I have found some really, really interesting material. So let's have a look here at this one, just to really draw the point home. So he's going to start, we're going to talk about these circular waveforms, okay? And you notice of different frequencies, he's adding these waves of different frequencies and how they trace the various shapes based on the unit circle. Okay, if you add enough of them, it really starts looking like the sawtooth wave. Okay. And there's another one quite nice as well. We did sawtooth. We can look at the square wave as well. It's a similar sort of process. A single sinusoid, and then there's a second one at looks like twice the frequency, or 3 times maybe. Yeah, really beautiful animations. It really helps us sort of visualize how things go. Okay, so and we'll get into the unit circle a little bit more, but I'll just introduce it here. So the idea is that you can follow a circle, and it will trace the values in this sinusoidal fashion. That's how we get that classic sine wave shape right there. So we follow the x values here, or I mean, let's say we follow the y values. If we think about what we call the time domain, if we think about the x-axis as time, and as we go forward in time slightly, just watch the red line, and this is the pattern with which the y, or amplitude, in our time domain will change, right? So if we trace a sine curve, or we trace a circle, it resolves into the sinusoidal curve, right? So as we go from negative, whatever you want to call it, I guess negative 1x to positive 1x, y increases in a sinusoidal curve fashion, right? And decreases as well. So as we go, so if you think of, if you think the period is two of these up and then down, you get that classic fashion, okay? So that's the unit circle here. So if you have the size of the circle will be the amplitude, the speed at which it goes around the circle will be its frequency, and its a phase, or its initial phase, will be where it starts. If it starts from here and goes back around to there, that'll be its phase. And so there's another really nice guy that explains that as well, basically kind of says what I just said. And so you think about these circular paths in terms of understanding sinusoidal components. We often think about that shape, but if you think of that circular path, it becomes more clear. Some of the other stuff they're going to explain about the Fourier transform in terms of phase and complex numbers and such, which we'll get into. Okay, so what does he say here? Right. So how big is the circle? Amplitude, size of the radius. How fast do we draw it? The frequency. And where do we start? The phase. Okay, and so he has a similar animation here where there's the one cycle and then he adds a couple more, just like those animations we looked at. They're tracing different amplitudes and different frequencies. Okay, and in the end, you end up with something like this, where you trace these circles through that. They have different amplitudes, different frequencies, and you end up with a summed waveform in the time domain. So you end up, that summed waveform is the sum of these sinusoidal components, and this is basically what is going into our, desktop audio workstations, etc. This is the type of electric signal that's going to the speakers. We have, the cone out, the cone sucked in, the cone pushed out, the cone sucked in a little bit, sucked in more, sucked in a whole bunch more, pushed out a whole bunch more, sucked in, so you get that change in air pressure according to time. So air pressure or frequency being a component of time. Okay, so yeah, that's a like an over thorough explanation of these things, but it helps to be really, really thorough about these things to understand where all these things are derived from. Okay, so let's continue on with our main video here, and then again we'll stop at a certain point and probably go over these concepts again and again. But it helps.
So we know that representing a signal in the time domain is good because that's the way that it's going to behave in real life. But also representing it in the frequency domain is good in other situations when we're designing or analyzing a control system. And the Fourier transform gives us the ability to move from one domain to the other, which is awesome. Also, the other reason that I like Fourier transforms is that it's a stepping stone to the Laplace transform, which is even a more important tool in classical control theory, but I'll cover that in a future video. For now, let's finally dive into some of the math. If I was to give you these 2 points in the frequency domain and asked you to construct the time domain signal, how would you do it? This first point has a frequency of 1 Hz with amplitude of 1, and the second point has a frequency of 2 Hz with amplitude of 0.5, but neither signals are phase shifted. Well, since you know that these correspond to sinusoids, you'd probably write out a small equation like this. You'll see why I chose cosine instead of sines in a moment. But what you have are 2 separate sinusoids, and when you add them together, you'd get a result that looks something like this in the time domain. Now, I actually didn't plot this out ahead of time. I'm just kind of drawing this from what I expect it to look like, so it might not be exact. Now, if I added a third point, you'd have 3 cosines, and so on. However, it'll start to get really cumbersome if we use more than 3 points.
All right, so let's unpack that slightly. Let's look at these numbers. I'll shrink him here, but keep these figures up, okay? And I guess I'm going to have to pop out one of these things. So if we get our interactive unit circle there, I think I have actually a standalone version. Numbers, cosine 2 pi t. So 2 pi is the, in radians, it's the full circle, 360 degrees, right? So if we're doing 1 rotation per second, or time unit, it's going to be 2 pi, 1 full rotation, every time unit, or in terms of hertz, I guess, once per second. So we'll do 2 pi times t. If we have a frequency of 2 hertz, or 2 times a second, we're going to have 2 times 2 pi, or 2 rotations in 1 second, which will then be 4 pi times the unit of time, t. All right, and then 6 will be 3 hertz, so that's 3 times 2 pi, or 6 pi times the unit of time. All right, and since these are all linear systems, you can just add them all together. Not only can you add them, you take the frequency and you multiply that by its amplitude. So if this is amplitude of 1, it's just cosine 2 pi t, and if it's an amplitude of 0.5, these two amplitude 0.5, so it's 0.5 times the cosine of the 2 hertz one, and 5 of the 2 hertz one. Okay, and so that's going to give you that complex waveform. Let's see where it was at. Right, it's going to give you this added waveform together, okay, by adding those three components. Where do we go? Yeah. Okay. So this is where we're getting these numbers. That's cosine 4t. Right? It describes the waveform that's based on these components. But again, we don't have phase information yet. So let's continue on and see where that takes us.
So instead, I can reduce all of these summations into a discrete summation and add up all of the frequencies between negative infinity and positive infinity. But don't worry too much right now about negative frequencies. Just know that they're there. So I've rewritten the above equation in a more compact form. And this first term, A of nu, is all of the amplitudes at each of those given frequencies. And then each one would be multiplied by a cosine of that specific frequency. But what if I have a continuous spectrum of frequencies? Then you can just replace that discrete summation with an integral, and you can have an equation that looks something more like this. And now you should start to see that this is looking a lot similar to that inverse Fourier transform from above. And you can actually get a good sense of what the inverse Fourier transform is doing just by studying this equation. And you could stop right here, but we'll continue.
All right. Well, we'll go ahead and pause at least, and just go ahead and underline the fact that this is derived from this process, right? If we can look at this, all the units are there. The amplitude, or a sum of all the amplitudes from negative infinity to infinity, and the cosine of the 2 pi times the frequency and the unit of time, right? Okay. So essentially, that is mathematically almost describing the Fourier transform, in that you can take this, describes all the component parts, and we're going to use calculus here and take the integral, which means, you know, as we go from infinity to negative infinity, as we approach, if we do discrete points, we think, and you know, that's digital audio is a lot like that. If you take discrete points of this continuous signal, and you, let's say we have 10 points, you're going to get some approximation. If you have 20 points, you're going to get a better approximation. If you have infinity amount of points, you're going to get the continuous signal, right? And that will be described by that process of just adding all those points along these, all the composite frequency and component frequencies, and taking this integral and then adding them all together and making this sort of approximation of that continuous signal, really. Or, you know, an actual, as you approach infinity, an actual rendering of that continuous signal. All right.
Taking parameters like amplitude and multiplying them by sinusoids and adding them all up to get the signal in the time domain. And that's exactly what you did with the 2 or 3 cosines from earlier. But the equation still needs some work, and that's because we chose cosine waves that had 0 degrees of phase shift. But in general, signals can have sinusoids of any phase shift. Remember that phase and amplitude can be described by a single complex number, which is made up of real and imaginary components. And if we plot that complex number on a real imaginary plane, then the amplitude is the distance from the point to the origin. And phase is the angle of that line from the positive real line. When we do this, we see that a sinusoid with amplitude of 1 and no phase shift results in a point that lies on the real line, in this case 1, which is a real number, and a real number is exactly what we used in our example above, so it all works out. But for this next example, we're going to say that the sinusoid has a phase shift of 45 degrees and an amplitude of 1. And finding where this red dot is on the real imaginary plane is pretty straightforward. The amplitude is the hypotenuse of the right triangle, and the tangent of the phase is the imaginary part over the real part. And solving for these two equations gives us the square root of 2 over 2 for both the real and imaginary components. So now,
all right, let's take a little pause, and I think it's worth an extended sort of diving into imaginary and complex numbers and polar coordinates. And I find it useful. I still find it to be fairly daunting in trying to understand phase and stuff, the relationship between phase or XY, and then this I guess trigonometry, phase, cosine, sine, and such. So there's another really nice video which we'll go into. It's kind of it really describes things in detail. It's on the long side, but I think it's worth really delving in, and you can just skip this part, obviously.
Let's say that I have the complex number z, and in rectangular form, we can write it as -3 plus -3 plus 2i. So first, let's think about where this is on the complex plane. So this is our imaginary axis, and that is our real axis, And let's see, the real part is -3. So we could go 1, 2, 3 to the left of the origin. Let me space that out a little bit more evenly. So 1, 2, 3 to the left of the origin, so -3. And then we have 2i, so we're going to go up 2. So up 2 in the imaginary direction. So 1, 2, just like that. And so z is real part -3, imaginary part 2. Z would be right over here in the complex plane. So that is z right over there. Now what I want to think about are other ways to essentially specify the location of z. And in particular, instead of giving the real and imaginary parts, essentially the coordinates here, let's think about giving a direction and a distance to get to z. So for example, we could give the distance from the origin to z. So let's call this distance r. But that distance by itself isn't enough to say where z is. You have to say, in what direction do you have to go a distance of r to get to z? And so to specify the direction, we will have this angle theta in radians, this angle between the positive real axis and this line right over here, this line or the segment that connects the origin and z. So if someone gave you this angle and this distance, then you could get to z. Now what I want you to do right now is pause this video and see if you can find a relationship between r theta and -3 and 2. In fact, given this complex number in rectangular form, can you figure out what r and theta are? Well, let's think through this a little bit. And to help us that, let's remind ourselves of the unit circle definition of trig functions, because we are going to use some trig functions to relate r theta and 2 and -3. So I'm going to construct a unit circle here. So construct a unit circle. So this right here is a unit circle, circle of radius 1. So construct a unit circle. That's a unit circle. So by definition, what are the horizontal and vertical coordinates of this point right over here, where this line intersects the unit circle? Well, this is forming an angle of theta with the positive real axis. And so the horizontal coordinate over here, by definition, is going to be cosine of theta. Cosine of theta. That's the unit circle definition of cosine of theta. And the vertical coordinate is going to be sine of theta. Sine of theta. And so what would the horizontal and vertical coordinates of this point be? We obviously know they're -3 and they're 2, but what would they be in terms of cosine theta and sine of theta? Well, look, this point right over here is a radius of 1 away from the origin. So this distance right over here, that distance right over here is 1. But now we are r away from the origin, where r times as far. So for r times as far in that direction, then we're going to be r times as far in the vertical direction and r times as far in the horizontal direction. We're going to have to scale we're going to scale everything by r. So the horizontal coordinate of this point right over here, instead of it being cosine of theta, it's going to be r times cosine of theta. So this point right over here, which we know is -3, is going to be equal to r cosine of theta. And by the same logic, this point over here, the vertical coordinate, we're going to scale up sine theta by r, where r times is far. So this point right over here is going to be r sine theta. And we already know that that's equal to 2. R sine theta. So given that, can we now figure out what r and theta are? So let's first first think about figuring out what theta is. So to do that, let's think about some of our trig functions. So one trig function that involves sine theta and cosine theta is tangent theta. So for example, we could say tangent theta, tangent of our angle, tangent of theta is equal to sine of theta over cosine of theta But we could also multiply the numerator and denominator here by r. That won't change the value. So that's the same thing as r sine theta over r cosine of theta. And we know r sine theta is going to be equal to 2. And we know that r cosine of theta is negative 3. So this whole thing is going to be negative 2/3. Another way of thinking about it is the tangent of tangent of theta is going to be the same thing as the slope of this line right over here. And what's the slope of that line? Well, if you start at z and you want to go to the origin, you're going to go positive 3 in the x direction, and then you're going to go negative 2, or as you could say positive 3 in the horizontal direction, and then you go negative 2 in the vertical direction. So the slope is your change in vertical over change in horizontal. It's negative 2 over 3. Negative 2 over 3. But now we can use this to solve for theta. To solve for theta, we just take the inverse tangent of both sides. And we get theta is equal to inverse tangent of negative 2/3 of this thing right over here. So let me copy and paste that. And we can get our calculator out to figure out what this actually is. So let's turn it on. Let me make sure that I am in radian mode. I am. And so I can take the inverse tangent of negative 2 divided by 3, which gets us negative 0.58800, on and on and on. So if we round to the nearest hundredth of a radian, it'd be negative 0.59. So this is approximately negative 0.59. Now, is this the right angle? Is this the theta? Is this the theta that we are looking for? Well, this theta, negative 0.59, that's going to get us over here. That's this angle right over here. That's what the inverse tangent gave us. And it makes sense because this ray is a continuation of this ray right over here. Together they would form a line. It has the same slope. But that's not the theta that we are looking for. The theta that we are looking for is going in the opposite direction. It's halfway around the circle. So if we think in terms of radians, it's going to be this angle plus pi radians. So the theta that we're looking for isn't 0. It isn't going to be what our calculator gives us for this. It's going to be this value plus pi. So theta, the theta that we care about, is going to be negative 0.59 roughly plus pi. Let me say approximately, just because I have rounded right over here. So let's get the calculator out. So let's take our previous response, and that's just the previous answer, plus pi, because we're going to go in the opposite direction. So that gives us roughly 2.55 radians. So this is approximately 2.55 radians is our claim for what theta is. Now, does that make sense that this angle right over here is 2.55 radians? Well, this angle, if we go straight up, that's pi over 2 radians, and pi is 3.14, so that's going to be 1.57, right? 1 point something like that. And this is pi radians, so that's 3.14. 159, keep going on and on and on. So 2.55 is indeed in the right quadrant. So that is right. This is going to be an angle of 2.55 radians. Now we just have to figure out the length, what r is. And that we can just use the Pythagorean theorem for. We could set up a right triangle. We know that this distance right over here is 2, because this distance right over here is 2. And we know that this distance is, the coordinate here is negative 3, but the distance here is just 3. So we know from the Pythagorean theorem that r squared is equal to 2 squared plus 3 squared or that r is equal to the square root of 4 plus 9, which is 13. And so there we have it. We have -3. So we know r is equal to the square root of 13, and theta is 2.55 radians. So using that information, we can now rewrite z in terms of r and our theta. So now we can say that z is equal to, instead of -3, we can write it as r cosine theta. So we can rewrite it as square root of 13 times the cosine of theta, which is, we're saying theta is roughly 2.55 if we round to the nearest hundredths, plus 2, we already know is r sine of theta. So r is square root of 13, and then sine of theta, 2.55. And then all of this we could say, or all of this is going to be multiplied times I. And if we like to simplify it a little bit, or to kind of really make clear what the r is here, we could factor it out. So we could say that z is equal to square root of 13 times cosine of 2.55. And once again, 2.55 is an approximation, so maybe I should say approximately equal to cosine of 2.55 plus, I'll throw the I in front, plus I times sine of 2.55. And so when I rewrote z in this format right over here, it makes it much clearer what the direction I have to go in is. The direction is 2.55 radians counterclockwise from the positive real axis. And it also says how far I need to go. I need to go square root of 13. So this essentially makes the polar, it makes it clearer how we get there in kind of a more, I guess you could say, polar mindset. And that's why this form of the complex number, writing it this way, is called rectangular form, while writing it this way is called polar form.
Okay, great. So yeah, that was a very detailed explanation, and I think that works really well, and it sort of gives us this idea of the two sides of the coin, of the Fourier transform, the time domain and the frequency domain. We can describe these points, these circle points, which we explored in our unit circle. We can describe all these points along the unit circle, along our waveform, both in terms of what he describes as rectangular coordinates, okay, the x and y axis, the real and imaginary parts, but also in terms of polar coordinates, which are a factor of the angle and the radius there. Okay, so if we continue on here, you'll notice that these equations are derivative of what we just learned about in that polar rectangular complex number.
Now we have
tutorial.
complex signal information that captures both phase and amplitude, not just amplitude like we had with the real number. And I'll change my a of nu function, which only had amplitude information, into a function of nu, which contains both amplitude and phase. Additionally, we can describe sines and cosines in the complex plane using Euler's formula, which can be written like this: e to the it equals the cosine of t plus I times the sine of t. So now, with the added phase information and writing things in the complex form, amplitude times the cosine becomes the function of nu times Euler's formula. And this new equation can handle complex inputs. All right, so let's continue our example of a cosine signal with amplitude of 1 and phase shift of 45 degrees. And remember, that corresponds to the square root of 2 for both the real and imaginary component for f of nu, which is written at the top of the screen. So if I multiply out this equation, I'm left with 4 separate terms. The first 2 are real numbers, and the last 2 are imaginary. So wait, what does imaginary time even mean? Well, it really doesn't mean anything in our case, and that's where negative frequencies come in to help us. The imaginary time signals are going to cancel out when you consider the negative frequencies. Remember, we're summing all frequencies between negative infinity and positive infinity, and so far we've only looked at the positive 1 Hz, so we need to add this to the results of the negative 1 Hz. Now at this point I have a small side note. The function f of nu is complex, as I've stated earlier, but if you were to plot the real component of f of nu and the imaginary component separately, you would find that the following is always true when dealing with real-time problems. The real component would be an even function, and the imaginary component would be an odd function. And what I mean by that is that the real value between a positive frequency and its negative counterpart would have the same value and the same sign. And the imaginary value between the two would have the same value, but opposite signs. Also, the values of each is split between the positive and negative values, so they would each be half of the original. So in our case, we would have frequency content that looked like this, with square root of 2 over 4, once we realize that only half of the signal is captured in the positive frequencies and the other half in the negative. So we already have the positive frequency content, although the amplitude is actually half of what I wrote earlier. So let's generate the negative frequency values. And when we sum these two results together, you're going to see that the imaginary parts cancel out and the real parts add together. I'll let you work that out and make sure that it's correct. But if you have any problems with it, leave a question in the comment section below and I'll try to address it. So what you should be left with, though, is a signal that contains both a sine wave and a cosine wave. And this further reduces to a single cosine wave with a phase shift, and that phase shift is 45 degrees, which is exactly what we intended from the beginning. So it all worked out. But that really seemed like it took a lot of effort to get to this point, right? Well, really it isn't. Because using the Fourier transform as an integral, you don't have to work through all of those steps individually like we just did. It takes care of all of that for you. Now in most cases this integral might be difficult to actually perform, but I'll leave that up to the math department to explain how to go through all of that. What I really wanted to do is just give you an understanding of how the Fourier transform works. So just to sum it up, we can write the transformation from the frequency domain to the time domain like this. You take a continuous set of frequency information, and this is complex information since it has both amplitude and phase. We call that information f of nu. Then you multiply that by Euler's formula, or by a bunch of phase-shifted cosine waves, with frequencies ranging from negative infinity to infinity. Then finally you just sum up each of those waves at all of those frequencies, and what you're left with is the time domain signal. So now you can see that the inverse Fourier transform is really as intuitive as multiplication and summing, since that's all it's really doing. Now I had intended to cover both the inverse Fourier transform and the forward Fourier transform in the same video. Unfortunately I got writing too much and now I've run out of time. Therefore this is only part 1 of the video, and in part 2 I'll cover the forward direction of the Fourier transform, along with a simple way to remember it. Don't forget to subscribe so you don't miss.
Okay, so great. Thank you very much, Mr. Douglas. That's very helpful, I think, in trying to understand slightly a more mathematically informed understanding of this Fourier transform. Okay, so once again, I'll bring us back to these few videos here. This idea that we have a time domain complex wave, a summated wave. This sends a square wave, and then it can be broken down into its component parts, into individual sinusoids at different frequencies, and then each of these sinusoids can be described by the 3 factors of frequency, how fast it's going, its relative amplitude, and its phase. Okay, so when you talk about Fourier transform, we're looking at, in the frequency domain, we're looking at this. We're looking at this linear complex waveform, the summed waveform. So going back again here to these functions, we get a single linear waveform that is a sum of these waveforms of the component parts. But we can break it down into the component parts like this and have each of the component parts be represented by phase, frequency, and phase, frequency, and amplitude. Okay, so it's these two sides of the coin, both representing exactly the same thing, which can be very helpful. So let's just jump into and then, well, let me just also underline the fact that we can then, describe these. Well, here's, let's have another look at that, which is really nice, the square wave, which is basically what he was dealing with. If we think about in terms of frequency, amplitude, so these smaller circles, smaller amplitudes, faster frequencies, and different phase relationships with all the other ones, okay? And then it creates this complex square wave. So if we were to take that to infinity, it would be more or less sort of perfectly square. That's where we get the square wave, all right? And then again, if we go back to this idea of polar and rectangular coordinates, each of those points along the circle can be described by the phase and the amplitude, right? But also can be described by its xy, so its frequency or its amplitude over time, all right? So that's how we have, two sides of those coins. Just kind of interesting. So let's just open up Super Collider there and just take a look at some of these. I have a couple things prepared, and just to give you an idea of how it works out practically, we have, let's see, something like this, a Spectral Vocoder, okay? So you'll notice now these PV objects, I think, these Josh Eugens, I think it's Josh, are great, fantastic, and Phase Vocoder, and I think they're in the SE3 plugins suite, so you just install that. I know for Mac there's binaries out there, and I think I put it in an earlier video. But the idea that we can follow along where we're doing this kind of spectral processing, and there's a whole slew of these. So, but we can follow, we have these buffers, and the PV series of plugins very nicely allows you to, within the SynthDef, allocate a buffer locally here on the fly. So we have buffers to store our information. And what we do then is we take the saw wave, and we take the forward Fourier transform, an FFT. So we convert the saw wave from the time domain, from its time amplitude over time description, into its a frequency domain using this function, okay? And so then it becomes a collection of sinusoids with descriptions of phase, amplitude, and frequency, all right? And then we also take another FFT of, in this case, we're taking the sound in, okay? And so we convert from time domain to frequency domain, both of our sounds that we're dealing with. And then we run some kind of function on it in the frequency domain. So if we do that, we can see this maps the spectral envelope of one process onto another. And like I said, there's loads of these really nice PV objects. I think if we just do a search for PV. Oops. Right, there's loads of these here. Can copy phase and magnitudes. We can do this onset detection, pass bins, freeze magnitudes, spectral morphing, etc., etc. But so you're then doing some manipulation in the frequency domain. In this case, we're taking one spectra, and we're mapping it onto the other one. So it has a sort of vocoder effect, where it's kind of a carrier modulator type of effect. The sound in being the modulator and the saw being carrier. And then once that process has taken place, then we do the inverse Fourier transform, IFFT, and we change it back from the frequency domain back into the time domain, because that's what our Eugens like out and etc. expect. They expect that complex waveform in the time domain. Okay, but again, since they're identical, the frequency and time domain, but they give us a different type of manipulative possibilities, then so we can manipulate things in the frequency domain. So I think this is, I'm going to have a separate video actually just to go through this, but we might as well play something here. I think we have, yeah. Okay, so it's kind of working there. So you see it's mapping my voice onto the sawtooth wave and has that kind of vocoder effect. And then, there's loads of these other ones. And if you take any of these, max smooth, max smear, what was the one I wanted to look at? I think copy phase, morph. So PV morph, if we look at it, and I'll just grab all this over so we can look at it slightly bigger. Look at these examples. It's the same sort of format. We do an FFT on them. We do some kind of morph. Which is it doesn't explain what it is. Spectral morphing. Okay, so it morphs one to another, and then we do an IFFT. Takes it back out to the time domain. Okay, so that was kind of a real trying to give a layman's explanation of the Fourier transform and its sort of importance and its usefulness in audio processing. And if you take things into the spectral domain, you can do all kinds of manipulations there. And this PV series gives you a bunch of different combinations. And just understanding the chain of events there. So, in fact, if I wanted to do morph and spectral map, I would do things in the frequency domain. So I would, FFT these. I could do a spectral map, and then these are still in the frequency domain. I can do a spectral morph after that. So then after the map, I can morph that thing. So I would take chain one in, for example, which has been mapped, and then maybe another FFT object. I can take yet another object here, whatever. I can do 3, for example, and have it equal FFT, and it could be some kind of, buff C, and it could be something else. So we'd make a buff C, etc. I'm just, sort of pseudo-coding it here. And then, take some other sound that could be a play buff. Play some kind of buffer. And we take that, and then we just chain 3 there, and then have another process yet on morph. So mapped, morph to something else. And then finally, the last part of the chain would be to take the inverse Fourier transform, bring it back out into the time domain, and then stick it out. Okay? Out the speaker. Okay, so just to give you some background and an understanding of how Fourier transformation takes place, and you get really nice, loads of nice and really interesting effects and tons to play with anyway in that thing. So I hope that was helpful a little bit. I know it was for me. These things tend to be really daunting and, kind of banging up your head against the wall if you don't have a lot of maths or you don't have a sort of comfort around math. Again, this idea of the complex, not the complex, but the time domain versus the frequency domain, and how we use the beauty of the way unit circles work and the way polar and rectangular coordinates work to easily slide between the two different domains. Okay, well, hopefully that was helpful, and good luck with that and with all your Fourier transformations.